Okay, in this next clip we're going to talk about producing robust programs. Now, there's a few things that we need to talk about here. Firstly, you need to be able to describe you need to know what defensive design means. Well, defensive design is about making sure that what you've programmed is, secure, that it's safe, it's robust, So how would you do that sort of thing? Well, you might use authentication to check the identity of the user. You might use passwords to prevent unauthorized access to things. You might require specific usernames or passwords for certain things. So you might limit functionality for certain people. You might give better functionality to other people. You might plan for users making mistakes. So giving them a certain number of times to get that username and password correct, or if they hit the wrong key and something happens, or users trying to access parts of a program or a program that they should not do. So defensive design is about making sure that the program works as it should do for the level of person that's using it, and doesn't give them access to things that they shouldn't do, and doesn't let them do things that they shouldn't do. Okay, and operating systems are a great example of that. Windows can be locked down to a specific user of a specific age range, and what it lets them do can be different to someone who's got administrative rights. Okay, so just think about those things on the defensive design thing. The next thing we need to talk about is program maintainability. A well-maintained program is easy to understand by other programmers. So when we've created programs in class and we've looked at Python and we've used annotations, for example, annotations and the layout of your code, the way that you've structured it, makes it easy for people to understand. That means that they can access it and they can edit it, and that's important if you're working in a team of programmers, that your programming isn't done in a way that it doesn't make sense to anybody else. It can be revised, it can be updated, it can be tweaked, it can be debugged, those sorts of things. And also, when you're in that development process, excuse me, using that iterative design process and saving with different version numbers. You'll see this with apps. The version number, when it's a small update, changes by a decimal place. When it's a big update, like with iOS, this year we'll get iOS 13. But then there'll be 13.1 and 13.11 and stuff like that. So ways you can make your program maintainable with those comments. Using indentation helps, because it just breaks up what the code looks like. You can see when something's indented. Sorry about the bell. When something's indented, it tells you with selection, for example, if and else, what's going to happen if you get into that bit of the program, or if it's with a loop or while loop, what's the bit that's indented. You can see, well, that's the program within that loop, or if it's a subroutine, that's the program within that little subprogram. Using variables, another bit of program maintainability is using variable names that just make sense, that are obvious. It's no good saying bananas equals input, what is your name? It should be name, shouldn't it? And don't forget, a variable is just the identifier for a bit of memory where something is stored that might be used in the program and can be changed. And obviously the use of subroutines, because what that does is it reduces the amount of code you're going to need. Means you don't have to duplicate things over and over again, and again makes the program easy to look at and easy to understand. The next thing to think about is testing and test data, something that we know about from our NEA task. Obviously it's essential that a program gets tested fully before others use it. And you'll see where that hasn't happened in the real world, or where it hasn't been tested thoroughly enough and software comes out with bugs in it. A recent one was FaceTime, the group FaceTime bug, where Apple had to shut FaceTime down, the group option anyway, for a period of time, because it turned out that when you called somebody up in a group FaceTime, you could hear what they were saying before they answered the call. So making sure things are tested properly, making sure they're tested on the devices that it's intended to run on, really important. Effective testing checks all the functionality, repairs potential errors before the external user gets to use the program. And different types of testing include, do different things. So, I talked before about iterative design. Iterative testing, a cycle of, design, development and test, design, development and test, where results of testing are fed back into a loop, and you tweak the code and you improve it, maybe make it a bit more efficient, maybe make it work if it didn't do, and then you test again. That final testing, where you think where you're using it like the end user's going to use it, to see if it does everything that it should do in the way that it should do. You know, you might do usability testing. Is the program easy to use? Is the user interface user friendly? You know, is it going to appeal to the target audience? Will they be able to use the program? You know, one of the things that I struggle with if I ever pick up a form of Android on it is I'm so used to iOS that I don't find it easy to use straight away. You know, there's a different layout. And if you've ever gone from Windows to a Mac OS, for example, you know, just the different layouts of things and the different way that you select things can, you know, that's a usability issue. So is it easy to use? Is it secure? So you'll do security testing, you know, to check that the program isn't vulnerable to attacks, you know, and that the data that you might put in there is held securely. And then you might do some load and stress testing, you know. Will the program crash if multiple users access it at the same time? You know, what if you want to multitask 500 things? You know, can it do that? What happens if you get to 501? You know, stress testing it and loading it up and seeing what it can cope with to make sure that it's going to do what it should typically be able to do. Okay, two more little bits on this section. Spotting program errors. Obviously, you'll know from writing Python the IDLE, you know, gives you error codes. You know, if it says that you've got a syntax error, it means usually that there's an error somewhere in the code. It might be a bracket, it might be a speech mark, it might be a colon, it might be indentation. You know, but a syntax error in an English lesson is not using a capital letter, not using a comma correctly or a full stop. In coding, it's not spacing properly, it's not using those different symbols like the colon properly and things like that. Or there might be a logical error, you know, where there's just a plain fault in the structure of the code or the design of the code. Say, for example, you know, you've done greater than instead of less than. That's a really basic example, you know. Or you've done while true, while false instead of while true. So, you know, the program, whilst there's not a syntax error, you've not typed anything wrong, it's just not going to run as it should do. So the two main errors to think about are the syntax and the logical errors. And then finally, you know, just going back to testing, it's about test plans and test data. You know, when you start testing something, you've got to have a plan. Usually you would start that plan off before you even made the program, so that you know what's the bare minimum this thing needs to be able to do to be a success. And then as you go along, you know, you'd probably think of other tests that would get put in there. Once you know what your tests are, you need test data. And test data is not just typing in what you think people are going to type in. That's normal data. You've got to check that that works. But you need to do some extreme data as well, or sometimes boundary data. You know, so can that program handle somebody saying that they're 115 years old? When, you know, that's a very rare age to put in there. Or, you know, can it handle somebody putting, well, I can't think of another example, but that will do. I think you might also put in some erroneous data as well. What happens if you put an answer in that can't possibly be true? Does the program recognise that and do something about it, or does it just accept it? And is that eventually then going to lead to a bigger problem later down the line? So in this section, we've talked about defensive design, using authentication, passwords, user access to make a program secure. We've talked about program maintainability, when you're writing that program with annotations, comments, indentation, variables and subroutines. We've talked about testing and test data, and about test plans and test data, particularly normal data, that extreme, on the edge of what might be okay, and boundary data and erroneous data. We've talked about those different types of tests, iterative testing, final testing and so on. And then we've talked about the sort of errors you might get. The two main ones being that syntax error where you've written the code wrong, and a logical error where you've made a mistake that doesn't stop the program from running, but might stop it from running in the way that you intend it to. And that's the end of that clip in just under 9 minutes. How about that?